goes from pi to 2 pi? 0 to 2 pi, right? So 0 all the way back around to 2 pi. What else do you know? 1 unit high, 1 unit wide, 1 unit long, right? Radius of 1. What that means for the y is we only need 1 unit because it's not going to go higher than 1 and it's not going to go lower than -1. That's why it's a fairly short y-axis. Now our units on the x-axis aren't going to be 1, 2, 3, 4 like a normal graph. What we're going to use is 0, pi on 2, pi, 3 pi on 2, and 2 pi. And why are those going to be our x-coordinates? Because those are the axes around the circle. Bless you. So let's start at 0. What is the sine value of 0? So look at your little unit circle. We're on the right-hand side. 0. What's the sine value at pi on 2? So top of the circle. Sine value at pi. Sine value at 3 pi on 2, bottom of the circle. Sine of 2 pi. Now what if I added ticky marks in between these? Okay, so I'm just going halfway between the units we just put in. Well, what's halfway between 0 and pi on 2? So what's half of the first quadrant? Pi on 4. And what's the sine value of pi on 4? And let's get the decimal value for that, because I don't want to have to start doing root 2 on 2. So someone who's got their cal candy, do root 2 divided by 2, tell us what the decimal value is. Sorry, 0.7 if we round to 1 decimal place. Confirm. Okay, so 0.7 is going to be more than halfway closer to 1. Well, what if I put a little ticky between 0 and that pi on 4? So now I'm splitting it even further. What's halfway between 0 and pi on 4? Pi on 6. Somebody want to confirm that? Okay, and what's the sine value of pi on 6? Sine value of pi on 6. A half, so that's going to be halfway in the space. And now I'm going to put a little tick between our pi on 4 and our pi on 2. Okay, so that's got to be our pi on 3. And what's the sine value of pi on 3? Okay, and someone get the decimal value. So 0.9 if we round. Confirm. Okay, so closer to 1 than our other point. And what's going to happen in quadrant 2? Exact same values but reversed. Are they positive or negative in quadrant 2? So sine is positive. So we know that they're all going to be above the x-axis. Okay, between pi and 3 pi on 2 is quadrant 3. So we know they're the same values as quadrant 1 and 2, except they are negative. So they're going to be below the x-axis. And between 3 pi on 2 and 2 pi is quadrant 4. So they are going to be negative, so below the x-axis. Here's what sine looks like. Let's pretend in quadrant 2 I actually hit those points. Let's just pretend. Bless you. Those of you who have done physics and have done waves in physics, this is probably not a surprise, because sine waves are sound waves, they're water waves, it's all to do with trigonometry. And later on in this unit, we're going to do all the applications, which will look at how does physics use all of this. And if you're not a physics person, that's okay, I'll teach you everything you need to know. If I were to take this half of the graph, so quadrant 3 and 4, and I were to just move it here underneath quadrant 1 and 2, what shape would it make? Kind of a circle-y shape. So sometimes this is hard for people to see because what we're doing really is graphing the unit circle, but we need to do it in relation to time. And when you graph the unit circle in relation to time is we can't go backwards because you can't have negative time. So take a look at this video that's going to graph the unit circle circular circular, and at the same I don't want you to see it yet. It's going to do a circle, and it's going to do the graph at the same time. We don't need the lights because it's really short. It's like 29 seconds. Okay, so watch what's going to happen here. So you're going to see the point going around the circle, and then it's drawing it in time onto the axes themselves. So there's the end of Q2. Now we're into Q3 and Q4. Isn't that kind of cool? So all this represents in terms of the graph is just one revolution of the circle. It's just what cos happens to look like. Grab a red pen. Easiest way to do this is just to look at the axes values, and I just memorize them in order so we know that it goes 0, 1, 0, minus 1, 0. You don't need to actually plot the pi on 3s and pi on 4s and pi on 6s. If you just do the 4 or 5 points, 0, 1, 0, negative 1, 0, you'll get the perfect sine curve. Okay, I just wanted to show you why they were what they were in quadrant 1, 2, 3, 4. Domain and range. Domain and range. Okay, so why is it all real numbers for the domain? It stops here. But in theory, we know that you can go backwards around the circle, and we know this goes on forever because that would just be more revolutions of the circle. So the domain is XER, or negative infinity to infinity if you like that better. What about the range? Okay, and if I want to match my XER, how do I write between 1 and negative 1?
1 is less than, or negative 1 is less than, y is less than 1.
Okay, so that's what I heard. Do we want to confirm or do we want to change? Or equal to. So negative 1 less than y, less than or equal to y, less than or equal to 1. If you want to match the negative infinity to infinity, the range is negative 1, 1 with, which we call them brackets. Remember, square ones are just brackets. Okay. This makes sense because of the unit circle. You can't go over 1 or under 1 because that's the maximum radius of the circle. Okay. On the same set of axes, we're going to do cos, so change colors. I don't care what color, just do it different than what you did sine. And so let's repeat the process. At 0, so right-hand side of the circle, what is the cos value? 1. Pi on 2, so top of the circle, 0. So pi, left-hand side of the circle. 3 pi over 2, I just felt like singing it in the song. 3 pi over 2, so bottom of the circle, 0. And we come all the way back around to 2 pi, and we're back at 1. Okay, just for the first one, let's go back and talk about the pi's and families and see. So if I go right in the middle of pi on 2 and 0, I have pi on 4. What's the cos value of pi on 4? Root 2 on 2. So it's got to be the exact same point where the sine is because the coordinates are the same. So the graphs will actually cross there. Okay, the first one is pi on 6. What's the cos value of pi on 6? And so that's the same as the sine value in pi on 3. So these two have to be the same height. Pi on 3, cos value is a half, so halfway in the space. Okay, so already we're getting this kind of down curve here. In quadrant 2, what do we know about cos? It's negative, so they're going to be below the axis. Quadrant 3, negative, so it's going to stay below the x-axis. And quadrant 4, positive. Take a look at them at 2 together, so sine and cos. What's the relationship between them? Kind of looks like DNA, yes, but in terms of the graph itself, what's the relationship between them? So if I were to take the cos graph, for example, and just slide it over, what would happen? It's the exact same as a sine graph. The cos graph is just a sine graph that's been translated horizontally. So sine and cos are actually the exact same function, they're just one quadrant apart. Think about that. They're the exact same function, they're just one quadrant apart. Again, you don't need to do all the points. I just memorized that it goes 0, 1, 0, -1, 0, 1. And that just comes right from the axes values. The domain, still XER, because we can have as many revolutions as we want. The range, still -1 less than equal to y less than equal to 1. And I'm just going to write that this was y equal to sine. And this was y equal to cos. No, cos starts at 1. Okay, let's look at funky tan. You've memorized your 5 values of tan. This is where they're going to come into play. Okay, so right-hand side of the circle, 0. What is the tan value? 0. Top of the circle, pi on 2. Undefined. How do we draw something that's undefined? Oh, we did. We did it last year with asymptotes. What's an asymptote? It's like we never taught you Unit 8 last year. Yeah, asymptotes are where we get undefined values or restrictions or non-permissible values, and that's where we put the dotted red line or the dashed red line. So graphically, that represents there's nothing there. It doesn't exist. It's impossible. Kind of remember that from last year? Okay, left-hand side of the circle, so pi, 0. Bottom of the circle, undefined, so we get another asymptote there. There's a t-shirt, I don't have it, but I should, that says, "Kiss my asymptotes, you mother function." That might get me in trouble wearing that to school. Back to the right-hand side of the circle, 0. Okay, well that does not give us much to work with. So let's do the in-betweens. Let's do the pi on 4 family. Okay, so tan of pi on 4, 1. In quadrant 2, so 3 pi on 4, -1. Quadrant 3, so 5 pi on 4, +1. And in quadrant 4, so 7 pi on 4, -1. Okay, let's do the pi on 6 family. Okay, so tan of the pi on 6 family, √3 on 3, so somebody's got a calculator, get us the decimal value of √3 on 3. .57, so 0.6 if we round, just looking for confirmation. Okay, so not quite to 1, a little bit more than halfway. Okay, and in quadrant 2, it's going to be the same value except negative. Okay, so not quite 1, less than half or more than halfway. And in quadrant 3, positive or negative? Positive, because tan's positive in Q3. And in Q4, and I know we've got Q2 wrong, and I don't know why. Can we double check Q2? I just know because it goes down. Q2. Yeah. No. Yeah, that's what I did. I put the ticky in the wrong spot. Ticky's got to be here. And this ticky two's got to be here. Thanks, Miss Hill. And our last family, pi on 3. So tan of pi on 3. Root 3, okay, so get me the decimal value of root 3. .7 confirmation. Okay, but I thought we couldn't be bigger than 1. Yeah, tan can be. It's only sine and cos because we're dividing by the hypotenuse. So we're okay, close to 2, but not quite at 2. Quadrant 2, it's going to be negative. Quadrant 3, it's going to be positive. And quadrant 4, it's going to be negative. Tan is a very cool graph. Watch this. Here's quadrant 1. Okay, so it's not connect the dots in a straight line. It's a swoop that comes up. Approaches the asymptote but doesn't cross. In quadrants 2 and 3, it swoops towards the asymptotes but doesn't cross. And in quadrant 4, it swoops towards the asymptote but doesn't cross. Grab your calc and look at how it does tan. If you don't have, just peek over someone's shoulder who does have, but not in a creepy way. Okay, we're just going to now do transformations. So I said the word translations, but that should have been stretches. So what do stretches and compressions look like? Base graph. Take away the numbers. What's the graph that's left? Sine, okay? If you want to use a unit circle, great. If you just want to memorize those points above, great. Either way, let's draw it together. Starts at 0, goes up 1, goes back to 0, goes down 1, and goes back to 0. These are always nice curves. They're not straight lines. We could. I just estimated in there, right? Like I said, you don't need to do all the pi on families because you know where they're going to be. Okay, what's the 2 in front? Is it inside brackets or outside brackets? Okay, so that's a vertical. Is it a reflection, a stretch compression, or a translation? How do we know it's a vertical stretch? Because it's whole number, so xy is going to go to x2y. So these are no different than other base graphs. They just happen to be trig base graphs. Going to my red pen. If you're a point person, you can still use the points. If you're not, we can just do it visually. So I'm just going to go in order left to right and multiply everything by 2. First y value is 0, so 0 times 2 stays exactly the same. The next y value is 1, 1 times 2. The third value is 0, 0 times 2. Negative 1 times 2. And 0 times 2. Okay, so join that. And these ones I find it's really easy to see is, did we grab this and yank it top to bottom? Yes, because the bumps are now twice as high. We didn't do domain and range for tan. Thanks, Kelsey. Let's go. Just, everyone good with this one before we domain and range for tan? What do we do with asymptotes? Oh, pink. Yeah, so we're going to start by saying x can be any number. But x cannot be, well, pi on 2 and 3 pi on 2. And where would the next asymptote be if we kept going? So this is 1 pi on 2 and 3 pi on 2. what would the next one be? So 1 on 2, 3 on 2, 5 pi on 2. So we're just going around the circle. The next one would be 7 pi on 2, and then 9, and then 11, and then 13. So what kind of numbers are those? 1, 3, 5, 7, 9. They're the odd numbers. So x cannot be, I'm going to use that k just like we did with the general solution, except this time it's pi on 2. And then I'm going to define k to be the odd integers. Ooh, I forgot the element of. I'm going to write that bigger so you can see it. K is an element of the odd integers. Sorry. You would put your negative infinity to infinity, comma, x cannot be blah, blah, blah. So just instead of this, you would have your negative infinity to infinity. Rest is exactly the same. Okay, so all numbers except every single time the pi on 2 is odd. It skips it, right? Because there's an asymptote there. Range. Okay, so if we look down, we got an arrow. We look up, we got an arrow. So if I want to match my one up here, is an element of the real numbers, or a negative infinity to infinity. Do you understand this? Okay. What's going to happen is people are going to put 2k pi k ez, because we did that so often in Unit 1 and 2. This is the only time that k is going to be an odd integer, is always with the domain of tan. No, because range, there are no asymptotes. Right, range is just every single value. Okay, what about reflections? Same steps as always. So strip away the numbers. What's the base graph? Base graph is 1, 0, negative 1, 0, 1. So again, you can just memorize that order, or you're just going around the unit circle and using the x coordinates. This time we have two transformations. What is the negative? xy goes to offer of x negative y. What's the 3? xy goes to offer of x3y. Confirm. What order? Left to right, so let's do the reflection first. Again, you can do the points, or you can just look at the numbers and change the sign. Okay, or you can do the ruler trick like before. Okay, so 1 is going to go to negative 1. 0 goes to 0. Negative 1 goes to 1. 3 pi on 2 at 0 goes to 0. And 1 goes to. And I find these are some of the easiest ones to do reflections. Okay, they're also easy to see, so can you see that you flipped it from top to bottom? Sorry? Is this our final graph? What do we still need to do? The times 3. So now I'm grabbing my red pen. Again, you can do points if you want to do points, or you can just do it visually. Okay, so I'm working off the second graph now. So I'm at negative 1 times 3, negative 3, 0 times 3, 1 times 3, 0 times 3, 0. And negative 1 times 3, negative 3. Again, these are some of the easiest ones to see that, yes, we have clearly grabbed this and stretched it out vertically. I want you to put your ruler on the x-axis, and I want you to draw a line through it. And it doesn't have to be red, I just had a red pen in my hand. Just some vocabulary, and again, if you've done physics and done waves, you should have heard these words before. And there's a slight typo in this, so I'm going to change it. So the height of a trig graph, and I actually want to put the word halfway between the max and the min. So we can go from the x-axis up to a max, or we can go x-axis down to a min. We can even do it on this side down to a min. So any of these heights are going to be all the same value. Okay, it doesn't matter if you're going up or going down. It's called the amplitude of the graph. And if you've never done physics, if you know anything about sound, what does amplitude mean? Right, how loud something is. Also amplify, right, the word amp. It all comes because these are sound waves. One width of the graph, so from min to min, or max to the next max, which is just off the graph, is called the period of the graph. Sometimes in physics they'll call it the cycle of the graph. Okay, same idea. Okay, so the height is called the amplitude, the width is called the period. That's going to come into play on Monday and Tuesday. How are you feeling so far? Good? Translations? Base graph. So take away the numbers, what's left? Cos, what does cos start with? 1, 0, -1, 0, 1. Let's identify the transformations. What's the 2? xy goes to offer of x2y. What's the +4? 4 units up. Okay, go ahead and do the VS. Is that better? I can zoom. Here is the vertical stretch. Okay, grab red, do the translation, which we might have to add some points to the top. Oh, we really need to add points to the top. Turn and talk about the domain and range. Turn and talk. Always have the red one, unless the question says for each one or the original one, but if the question doesn't specify, it's the last. Domain, or, that's never going to change for cos or sine. It's always going to be the domain. But that just means backwards revolutions around the circle, so we know we can go backwards. Range, so look down. Where's the lowest point on the red graph? Where's the highest point? 2 less than equal to y, less than equal to 6. And I just realized we made a mistake with our domain. No x in our equation. It has to be theta ER. That would be half mark off. Yeah. Oh, it matters to mathematicians big time. You're all, right. Doesn't matter if you did the other notation. Janae, did you just miss what we changed there? You missed it all. Yeah, why? Yeah, theta. Again, if you use a negative infinity to infinity, it shouldn't change. Just give me the range in the other notation. Bracket, 2 comma 6, and bracket. We have one more translation before we do the 3 inverses. Do you want to finish this one, quickly get it done before, or do you want to like stop now and do it when we come back? You want to pause? Okay, so we pause, we'll do this one, and then we just have the 3 inverses to do. And then y'all have the rest of the second class to work.